Let's start. Last time we've discussed the generative models, and one of them were variational autoencoder, and the other was generative adversarial network. And we will try both of these things today. We will build those models that we've seen. We've seen the animations and examples of work of these models, and today we will implement them and look how they work. So let's start. First, import those things we will need. For this, it's better to have a GPU-based runtime. I think Colab, of course, goes well. Now, here we put some models that we'll make use of. I think we've seen kind of these models before. At least flatten is, I think, conventional. Shape saver is conventional too. And then we will create some transforms for our models. And let's go to the data set. We will use MNIST from Torch Vision, and we will wrap it to the data loader to create our training loader. Then test loader is done in the same way. This is common stuff for every deep learning task. So now we have to implement the things that we described before. So variational autoencoder. Let's note how is it going. Whoa, do you have just a second? The slides from the last time. Oh, yeah. Okay. Yeah, I think I've trashed it. Okay. Okay. So, yeah, for example, I mean, I want to take the picture that we looked on the last time. Yeah, here it is. Yeah, so variational autoencoder is based on this idea. What should we do is we have to take data, pass it to encoder, and encoder produces two values. It's a mu expectation and the matrix. The matrix for our case will be diagonal one, and we will put one loss on this distribution. Then we sample here from random distribution from standard normal, and then we make it have the shapes that we want, and pass this value to decoder. This is an autoencoder, and decoder decodes the picture just like usual decoder. So what should we do? Is we have to first somehow move it to the latent space, then well, some lower dimensional representation, then predict mu and sigma, and then sample our random noise. So this is the model from NN module. First, we will need these buffers for our model. This is special methods of NN.module. They're used for creating variables of this model that they will be seen in parameters, and in our case it is not trainable parameters. If you remember the torch info or torch summary packages, we've seen number of trainable parameters, number of not trainable parameters. So these buffers will be counted as parameters of our new NM.module. So we define it as a standard normal distribution, so all zeros and all ones for variation. Then we will have just flatten encoder with some linear layers, activation, batch norms, dropouts. So pretty usual thing for us. Yeah, we've seen this before many times. That's why we will not stop it on it. So we build then encoder, and the encoder is producing some intermediate representation, and then we have two other parts of linear layers to predict this latent dimension. For this is a mu, so expectation, and logarithmic sigma. We will predict logarithmic sigma and then move it to sigma itself for convenience. And sequential, we will see the reason for that a bit later in the code. So the next step is an n.sequential as well for a decoder. And here we will do pretty much the same. Linear layer activation, batch norms, dropout, everything we know. Finally, sigmoid to have our values from 0 to 1. And finally, we'll restore the original shape to have the same shape of our data after autoencoding. And here is functions for convenience. First is encoding, and here we see that first we get latent representation, and these two produces expectation and sigma, and we return both of them. Then comes reparameterization trick. So this is where we create our new sample. So this step is reparameterization step. We are given sample, which is just a random number generated somehow by PyTorch random generator. And here we see our values. So, and here we see why do we predict logarithmic values, because after applying here a linear layer here in this expression predicts everything from -infinity to +infinity, and we could not have sigma negative. That's why we want it all to be positive, and we put exponent here, and that's how we create positive values only. Well, at least not negative, but in practice it will be positive. We won't predict zero because it will collapse all the network. And this is a concrete latent sample, and this is a reparameterization trick, so-called. And finally, let's make everything in one place. So first we encode and everything. Then we make a room for providing determined row sample. So if we want our model to be kind of more deterministic, or we want, for example, to reproduce results for one and the same random variables, for example, to track our training process and how values are changed over time. So for this, we reserve row sample, and if it is not provided, we just generate random sample from PyTorch. The next step, we reparameterize our data, and finally move it to decoder. So from this point of view, it's pretty much the same with the original, with regular encoder. So we have encode, decode, but in the middle we have this reparameterization. And finally, we return reconstructed object.
Can I ask a question?
Yeah, of course.
As soon as if you are working with 2D objects like figures, we can implement, instead of linear layers, we can do convolutional.
Yeah, convolutional autoencoders. Yeah, that's true.
Okay, so it's okay. And one more question. I see that the structure of encoder and decoder are more or less the same. They just go in opposite order. Is it like a rule of thumb, or, for example, I can do the encoder with convolutional network and decoder with a dense network, and regardless of that, neural net should study train parameters so that it should be okay, or it's still better to use the same structure for both of them?
Yeah. It's a rule of thumb to have them almost the same. Usually they're kept the same, encoders and decoders. We'll see it on the segmentation task, which I just recorded today, the lecture material for that. And speaking about the idea of having convolution layers and dense layers for encoder or vice versa is not a good idea, because the structure of your latent space depends on the constraints that you have in your layer. So when you convolve, you count locality. So your neighbors counts, and your not neighbors, some pixels that are far from this point, they don't count. And if you try to apply a linear encoder to this latent space, more or less you will fail. So they have different structure and different constraints on what could be done. But with convolutional decoder, for convolutional decoder, we will have to use transposed convolutions. So it's NN dot.
Yeah, of course, it will increase the size opposite way, in opposite way.
Yeah. It produces image of bigger size, but that's a good idea. More than that, speaking about real life GANs and VAEs, they usually use this structure, and one of the first GANs was DC GAN, so it was convolutional GAN. That's why it shined for some time when a style GAN was not here. But now it's a style GAN and a world of these things. Okay, so yeah. Okay, let's go on. So our autoencoder is okay. Then a bit of plotting. Have I run this cell? Okay, if I have not, I will do that. Here is just a simple function of visualization. Won't pay much attention to that. And here, let's look at what we have. What we have in our model. So it's a usual architecture, linear layers, many parameters for such data set, and many parameters as well for our data set. Oh, by the way, maybe I was, yeah, it doesn't count in total params number. I mean, those buffers that we had, they count somehow different. Okay, I think, yeah, I think we'll check it a bit. But still, we have plenty of parameters. Then, Kullback-Leibler divergence, the formulas that we've seen. Yeah, here it is written in the PyTorch. Let's make it a bit more readable. So what we do is O5 is just the weight, mean, sum, and here is the formula for Gaussian distribution. So mu squared plus log sigma and minus real sigma and minus 1. This is a formula just from a textbook on mathematical analysis. So now let's what do we do here? Or what do we do here? We take a batch, then we take predictions from our network, and we return concatenated version of that. This is made for visualizations. So we visualize latent space and reconstructed images. We will draw it here. So draw manifold, and this is what we've done on the what we've seen on the seminars. So last time, this is a manifold of our data, of our model, and currently it's not trained. That's why we see just noise. And we will see how it changes and how will it change. Then we'll have the callback that that uses this function of drawing manifold and getting test predictions for that. And later we will visualize that. Speaking about training, it's a usual one. So nothing special. We create our usual two stairs loops, and then we push our batch to our model, and we have prediction. We have some information about intermediate representation, concrete mu, concrete sigma, and latent spaces. And then what we need is to calculate Kullback-Leibler on that data, and that's the first part of our loss. So here mu and log sigma we'll make use of it. Then we calculate just quadratic loss of our cross entropy from our prediction and batch. Then we compute loss. This is normalization for our loss to be not very big. But in fact, it could be skipped now.
What was the sense to multiply and to divide?
Yeah. Here's, in fact, we could skip it.
Yeah, but anyway, probably it was some visualization or what?
Well, it's a matter of the balance between Kullback-Leibler and BC. So I mean, this is more, I think, like semantic way to weight them.
I see. So we try to make a noise which will be like loss function, the noise per pixel, and after that we multiply on the total area. Or what is that? 28 by 28.
We multiply by number of pixels, that we have, 28 to 28. What matters here is ratio between one part of the loss and another part of the loss. So I think a different notation could be just Kullback-Leibler plus C multiplied by BC. So I think this would be more convenient. But here we try to make this constant more or less semantic. So in real life, of course, we don't need to multiply by this. We usually just we change only this constant to, like, that's usual situation for multi-loss functions. So for multi-loss training process, one loss stands for one property of final model, and another loss stands for another property. Speaking about ways of choosing this constant, I usually do this the following thing. I train model without any additional stuff. In our case, it will be just BC. And then I usually do it in this way. So first I train only for this. So I don't constrain model on some properties. And then this value, I mean, when we train in this way, we get some loss value, absolute loss value. And then I add a second part of the loss, and I look how first line is compared to the second. So second line will be higher in terms of loss, yeah, because we added some loss, and we have to, so neural network and optimizers have to search for some balance between them. And I look at how this loss became bigger. And in this case, it's feasible to look at both parts of losses separately. So you monitor both sum of these, so just regular value of loss, but each loss separately could be monitored as well, and give you the idea on how they're balanced and who like pays more for the final result. So I think the idea is clear, yeah? How to deal with these two losses. So first, optimize the first one without additional complexity. This will be a baseline, and adding second loss, you will need to monitor that your values, your original loss won't get too big or too bigger than you wanted it to be. So if it increases twice, so maybe it's time to think about reweighting these things. Yeah. Speaking about the loss, so we calculate cumulative loss. Then we go backward, step, zeroing gradients, and remembering our data for visualization purposes. And then we print each epoch, each 5 epochs, we print what have we done. So let's run it. I have a graphical card here. We should wait for some time, but it will train now. After training the model, by the way, yeah, are you familiar with TQDM?
Sure.
Yeah, I think yes. Okay, so and the last step we will, so I have the result here already. I'll make it bigger. Yeah, this is a pretty small picture, well, low dimensional, low phi. And here we see how it increases. So our usual, well, some noise gets, like we have 9 here, 7 here, 8 here, 0 here, and here is once. Here is something, it is 3. Yeah, 3 is here. What else? What else? So I don't see anything distinct. Yeah. So we have trained the variational autoencoder on the MNIST data set. So here is the final state. And the same thing is for manifold. That's what we've seen last time on slides, and this is how we get it in practice. So first, just note, let's note that this this is the first thing. So classes are all together, and as the training goes by, it tries to grow. First, it explodes over -4 and +4, and then the second part of the loss comes to the game, and it tries to push it to standard normal distribution. And finally, we get the picture where every class is kind of compact, and overall distribution is something like standard normal. Yeah. So this is how two parts of the loss fight each other. First, the reconstruction loss comes into the game and rules, and on later stages, regularization of Kullback-Leibler divergence and distribution constraints rules the game. So basically, this is how variational autoencoder works. On the myfigs directory, you will have this animation saved, and I made it available to the node. Okay. Now let's move to the catalyst and to generative adversarial networks. So I think let's make a small break. I think I need some water to talk more. Yeah, just a minute, okay. Okay. So the next part is generative models is generative adversarial networks, and here the version of Catalyst is critical. So they changed the way they changed the architecture in latest versions. So let's use this one. And here we import everything we need. So why don't I see the visualization? Strange thing. So let's move here. Yeah, we do the same thing for creating data loaders, for example. Let's Okay. Well, oh, I see. Yeah, here is yeah, images. Yeah. Yeah, that's the reason. Okay. Haven't defined the matplotlib inline. Still okay. Okay. We still. Oh, I think I should do it after that. Do after that. Yeah. Okay. Let's make it this way. So we have created data loaders with MNIST data set, just like we did the last time. And here, since we need two parts of the GAN, first we define.
Can you please run the previous cells? There are some conflicts with the libraries. There is no get loader in util something.
Just like I said, 2106. Yeah, it's critical. I think in those files that are in the chat now, it's hard coded, because yeah, I noticed that reinstalling Catalyst doesn't work. They had data load kind of shortcuts for data loaders in the Catalyst itself, but they removed it now. Okay, let's start it from the scratch one more time. Catalyst 2106, important thing. Then check that everything works well. Go. Model Lieben line here, what I've fallen on. So regular NIST data set, and create some data loaders for that. And the next step is the generator. So discriminator. First, we need some feature extractor, and here it is a convolutional network. So we let's create. Yeah, this is how we want to train our generators and discriminators. And first, for discrimination, for discriminator, we need to predict binary labels. Is it from a real data set, or is it generated by a generator? This is a question, to be or not to be. First, convolutional layers with some poolings and activations, and then we have a linear layer which ends with dimension 1. So we predict binary output. Speaking about generation, first we need image size that we want to produce.
Can I ask you to stop seconds? What is the purpose of discriminator? It should just compare two different objects.
Yeah, just like we said on the last part. So what's the idea of generative adversarial networks? We first create some generated data from generator. We will implement it on the next step in our notebook. Then we generate some data from random noise, and we get this random noise just from any distribution. So we, in fact, we do not control how latent space is connected to generated images, in contrast with autoencoder. And the second part here is we take original images from real data set. And the goal of generator is to generate the pictures that are pictures of higher quality. So they are very similar to original images. So discriminator, to the point that discriminator will not sure, is it true data or is it a generated data? And discriminator have to distinguish one and other. This is a scheme of GANs. So discriminator solves binary problem. Is it came from real data set or is it from generated part of the data? And generator solves the problem of generation. From random noise, it have to produce something that will foolish discriminator. This is how we do. And yeah, from this
we have two variables, right? We have two images, right?
No, we have a batch of images.
I mean double batch. So batch of one, batch of generated and batch of two images.
No, they are concatenated.
Okay.
They are mixed. So the point is we provide both real images and generated at the same time.
Okay, I see.
Okay.
Just to make it harder for him.
yeah, to make it to make a discriminator learn both real data and generated data properties and distinguish them. So this is a usual classification. I mean, like cats and dogs, nothing more special than cats and dogs. But
yeah, I see.
But like real cats and broken cats. Yeah, I will show you some GANs output. Yeah, in the end of the seminar. Yeah, so it's a simple binary problem of distinguished real data and generated data. And we use convolutions just like we do usually with images and with classification, especially binary classification. It's very simple. And usually, speaking about GANs, we usually have discriminators more powerful than generators. Usually to train a GAN, we need to train generator for some steps, for 2, 5, 10 maybe steps of optimization, and then only one step for discriminator. This is a very very fragile balance between generator and discriminator, because if discriminator always distinguish, so if it distinguish 100% of one and other part, then generator won't learn anything, because everything generator do will be wrong from discriminator point of view. So we will speak about it a bit later, a bit down the stream. For now, the architecture is this, just simple binary classification of images. So the next step is generator. And for generator, as I said, we need first, as a hyperparameter, we need image size and lattice space size. This for us, it's 28 to 28, and 10, it's more than enough. We remember it, and then we will try to generate something out of it. For now, let's discuss this function makeup layer. Yeah. This sequential usual model, convolutional transpose is the layer that makes dimensions bigger. It's like a opposite to convolution is transpose convolution. It is called transpose convolution because this operation has matrix for this operation. It has matrix very similar to convolution, but it is transposed. We will see it on the upcoming lecture. Yeah, we will speak about segmentation, and there the transposed convolutions will rule everything. Then batch normalization, just a regular thing, activation, and convolution with batch normalization. So at this point, we have some bottleneck at the end. So first, we create some more sparse and highly more higher dimensional data, and then we squeeze it a bit to get neural network some space, kind of to maybe to dream, to have some intermediate representation with higher dimensions, to maybe how to interpret this, like, yeah, to make more space for model to adjust its parameters. And that's how our network is built. So first, and let's notice, we have input channels and output channels. So we have some input channels, and we create some bigger representation, and then we squeeze it a bit. So, and in this code, we see how we do our stuff. Yeah, we create 64 channels to 16 channels, and the representation goes, I mean, height and width of the image goes from 7 to 14. And when channels go from 16 to 4, we increase image size from 14 to 28. The later research shows that for better performance, we have to increase both the depth of our network, but we have to increase also number of channels and size of our feature maps. That's how efficient net works. Yeah, I will speak more about it in the lecture material, but for now, the main idea is we have many channels at the start. So let's look at this forward function. Yeah, so what do we have? We have some points, so some random seeds. This is how it could be interpreted. And then we, from these vectors, we generate map. And how do we do that? We first apply linear layer and then reshape. So just fully connected. So the random variables goes through fully connected layer and then are reshaped to 7 to 7 to 64 channels. And this is seed for convolutional part. And then we increase size of our image from 7 to 7 to 28, and simultaneously we decrease number of channels here. That's how it works, and it's kind of opposite to VGG, for example. So this classical approach were introduced in VGG when they tried to classify the picture. They first increased number of channels and then decreased size of the image. And here we do the opposite to this. And this is very fruity idea, in fact. And finally, we apply one convolution and sigmoid to predict fixed values, to produce values from 0 to 255 for final image. That's how generator is done. And as I said, we will train it step by step. Yeah, finally, yeah, forward is clear now. Makeup layer, I told about that. Any questions regarding generator at this step?
Why did you name it makeup? Makeup means maquillage?
No. Makeup, it's not. No, makeup as a one word is for doing something like drawing something on your face, and usually girls do that. Makeup is just prepare, just create. I mean, this makeup means just prepare, create, generate. You could check out the dictionary. I usually use. So, oh, we have something in the chat.
Oh, that's true.
What is lambda function?
It's like compound.
Okay, Yeah. I usually use Cambridge Dictionary, and it's so I think we could check this. Yeah. Okay. And the question from Isaac. What is lambda function from Catalyst? Do you ask for this? This is a layer. So layers, it applies some lambda function. So this is what it's supposed to be. Is it answers your question? So this is just a layer that applies this to every object that comes in. Yeah. So to whole batch. Here we have a batch size, and here we have the dimensions. It's just for convenience because you see in our later notebook, we did that. For example, here, flatten. Flatten is just a simple action of one transition, yeah, but we have to write the whole class for that. Very, very big notation, consuming lots of lanes of code, and this is just one lane.
But just to understand, it will be
it's just
one layer, or it will be more than one layer.
It is this expression is similar to something like that, like class lambda, and then dot model and def forward or return self x, and this for output. This is roughly the same.
Okay, got it.
So I mean, it just applies this lambda function to everything that comes in, and it is this class is a ancestor of an n.model. That's one thing, and another thing is let's check out. For example, I mean, if you don't know something, you just need to go to source code. For example, yeah, I think. Oh, you haven't discussed that the first year students. They are working on the Python course, and did you know that, for example, big number is, for example, 7 to 1,000. And this is what Python is capable of storing. Very, very big number, far bigger than int64, for example, which is default for a long representation of integers. And Python is able to store it and to process it. So they use large arithmetic or longer arithmetics. I will send the link to the chat, I think. I mean, I visited CPython implementation today to get more information about that. So the main idea here, don't hesitate to go to source code. And here I have the source code of Catalyst. Yeah, let's make it. What have we? Contrib.nn. So Catalyst, contrib, and then what else? Modules, llama. No, No, I'm not right. Lambda is from common, and common is here, lambda. Yeah. Okay. So what do we see? We see that this is a lambda function. We just store it, and then we just apply it. So what I expected. But the main idea here is that every library is written by some persons, by some human. So usually we use open source libraries. That's why we could check out what happens. We are not just blind in this world. Okay. A bit of coding exercises, and then yeah, speaking about generators, that's all. That's how generator works. So basically it takes random noise and it tries to produce something meaningful. Yeah. Let's move on. Then this is a catalyst callback for logging, for logging images to this directory. Yeah, but to this tag to the loggers that runner have. So usually it's a directory on disk, your local directory, but it could be also the yeah. Oh no, here is a tensor board. Okay, here is tensor board. I usually I used to use MLflow, but now I use ClearML for logging, but that's okay. And then more interesting things is generator and discriminator. We sample them with default parameters, and the next step here is we define two optimizers because, as I said, we want to train them separately. Yeah. So model for Catalyst, it will be one variable with different items. Yeah, and we define two different optimizers. First for generator parameters, and second for discriminator parameters. And for example, that's why we have a distinct operation of zero grad. Because in more complex situations that training just image classification, we need to trigger it in different scenarios. Yeah. First, we will we will create gradients for generator, for example, then from discriminator, and we don't want to mix these gradients between these two. Okay. So criterion is binary cross entropy. Yeah. And we have train data loader. This is what we do. Then some callbacks. It is for optimization, usual thing for Catalyst. Yeah, and our logging of figures of pictures that we have with our discriminator. So the next part is more interesting, and this is a custom deep learning runner. And the main functions that we need to implement here is handle batch. As I said before, Catalyst is a framework, so we don't have, like we did here, we just written one and the same pair of loops, of nested loops. Yeah, and for case of Catalyst, we don't need it. We just need to write one function which will be circled by already made infrastructure, and it will run everything right. So what we have here is a batch. The main thing is batch. And what do we want from it? first we want real images, then we want to get some latent size, and batch size tell us how many random vectors we want to generate. So we generate simple Gaussian noise for that, batch size to latent size. Yeah, so the same number of images, we will generate the same number of images that was taken from the data set, and we'll mix it, and this mixture will go to discriminator. Then we need to apply generator. Generator is called from random samples, and we get generated images. Then we combine them. As I said, we just concatenate, and we don't need to think about like mixing them, because every object of the batch is processed independently. That's why we don't care about sequence, about the order. We just put it one by one. It's not true for time series, for example, or for other models, but in this case, we could do that. Then we create labels for that, and for generated images it's a 1, and for real image it's a 0. So we will predict the falseness of the image. Then we pass it to discriminator. It's a simple classifier, binary classifier. Yeah, here we have predictions, and then we apply criterion to this too, for predictions and ground truth labels, which we generated a couple of lines before. Then we take those yeah, then we create one more batch for training generator. So here we created loss for discriminator, and this loss is for generator. And finally, we pass it batch metrics to our self.batch metrics storage. Yeah, and speaking about optimization step, we already defined it in our callbacks. So here you see that optimizer key is generator in this optimizer callback. So in this optimizer field, generator will be called, and it's a optimizer for generator parameters, and metric key is loss generator. And that's why we put batch metrics key loss generator. We put loss function calculated for generator. Yeah, and the same applies to discriminator. That's how it works. And since we put it here to batch metrics, so optimizer callback will do everything for us. It will 0 grads, no, 0 grads is before all of that. It will have, it will trigger backward, it will trigger optimization step, and so on. That's how we created gun runner. And this is the power of the framework, when we could just create one function, not carrying, not bothering ourselves with everything else. So by the way, I strongly suggest to use passlib. It's an advanced library, but it is in standard library of Python, but not everyone use it. It's object-oriented work with file names. And here we're launching TensorBoard. I think in my notebook it won't appear because of setup, but I think you will do everything. Yeah, because I don't have the ports needed, but still I could run training process with this. Oh yeah, I see. As last time, I don't have, I have two graphical cards here on this machine, and that's why Catalyst tries to tries to utilize both of them, and they're not compatible. That's why I have error of data parallel. But if you use it on Collab, it will run. And if I put the use PyTorch use CUDA devices to only 0, so for the first card, it will work, because it will Catalyst will think that I have only one card. So yeah, we have. I won't fix that in real time, but it runs, and in fact, it trains. The next step for today is ViaGun, just like we discussed on the seminar. I think you could do it on your own. Encoder is pretty much the same as we did before. Like it's an encoder for autoencoder part. So discriminator is pretty much the same. And we need, okay, so the picture, I think, yeah, this we need encoder, we need decoder generator, the same thing, and discriminator. And it's a more complex model. Yeah, I think if you're interested in this, you could dig into that. And what I wanted to show you today is other thing. Other thing is the following. This is what could be done with generative adversarial networks. I will send the link to Telegram chat. Yeah. No, it is not what we need. Yeah, you could open it yourself. So what do we have here? First, we have some black and white contour image, and the adversarial network generator of the network tries to oh no, it's yeah, it's a pix to pix. It's not the generator, but still it tries to generate the cat here, for example, and by the way, it runs in your browser. And if we clear, let's have it. I don't know what we will end up with, but it is something kind of kitty. Okay, I see. Think it needs eyes, maybe. So yeah, it distinguished some eye. So you could play with it more, and more than that, generative models. So yeah, this is another type of generative models when we have a mask and we have to generate something out of it. And here we have different colors. So network knows what type of things should it be. Should it be a window? Should it be a door or wall? And that's how the output is produced. Or simpler thing is shoes, handbags. So you could play with it a bit and read this paper that is related to this. In fact, in real life, it could be useful for generating, for example, levels of the game or something in this fashion. So we could write simple rules for generating such simple patterns, and the network will make more complex image out of it. Yeah, or we could just write simple map of some city, and a neural network will generate the concrete city for us. This is how it's done. So for today, that's all. I think you get more familiar with what GANs and VIES are. So thank you.
Thank you. Bye.
Goodbye.